Our next speaker is Ms. Siti Rahmah has a degree in microelectronics engineering from University Malaysia Perlis, UNIMAP, and a master's in science from University of Malaya. She's currently pursuing her PhD in advanced material characterization. She's currently a staff engineer for material analysis lab at MIMOS Semiconductor Sdn Bhd, and is responsible for lab operations to support analytical services requests from E&E industries and universities. She has more than 12 years experience in failure analysis and material and has worked in multinational companies. The topic will be on tools, technology, and techniques, advanced failure analysis case studies. With that introduction, I'll hand this session over to Ms. Siti. Over to you, Ms. Siti.
Thank you very much, Mr. Lawrence, for your kind introduction. I wish you a very good afternoon to everyone, and thank you for being with us in this webinar session. And for the next 30 minutes, I'll be sharing with you 5 different case studies using various sophisticated instruments for failure analysis and material characterization. So we hope that by sharing this case study, it will provide to you with an overview about the methods, techniques, equipments that are available in our laboratory that can assist to solve your analytical task. So here are the outlines of the case studies. Firstly, we will talk about a circuit modification for a reverse engineering purpose. Indeed, circuit modification can be a very complex process depending on the complexity of the device. Imagine if you have a metallization layer up to 7 or 9. So of course, the circuit modification process can be more complex as compared if you have only 1 or 2 metallization layers. Furthermore, there are thousands of transistors, resistors, and also other components in the device. However, in this case study, we will only show to you a simple circuitry for an example. And next, we will actually talk about the embedded defect analysis. Electronic devices typically are made of multi-layers, so embedded defect in between the layers can cause a serious reliability issue, and subsequently, it can cause a product failure. Therefore, it is important for us to understand the nature of the defect in order to avoid the occurrence in the future. So the case study number 3 is regarding a copper oxidation analysis. So this case study is quite interesting as it involves 9 different characterization techniques. From here, it tells you that sometimes you need more than one technique for us to study about the material. And for the case study number 4 and 5, they are actually related to a surface contamination analysis on the battery tap and also on a lead frame sample. Now let us start with the case study number 1, which is on the circuit modification. Well, first, what is circuit modification? So we can look at this example here. Imagine that we have this IC package. So inside this IC package, there is a silicon die. So basically, this silicon die has been designed and also fabricated. So circuit modification is to modify the circuitry of the fabricated IC device. Then, what do we need in order for us to do the circuit modification? For sure, we need to have the sample first, the layout, and most importantly, we must have the capability to perform this modification. And in this case, we are using focused ion beam instrument for the 3 purposes. First is to isolate or to cut the initial connection. Secondly is to make the new wiring. And third is to make the new probe pad so that the subsequent electrical measurement can be performed. So now let us try to understand a little bit about the layout. In this example, we will show to you the process of isolating a single resistors. So basically in this device, there are 3 resistors. As highlighted here, you can see the label R0, R1, and also R2. However, this layout is from the top view, so we are not able to see the metal stack. And therefore, I will illustrate to you the cross-sectional view of this device. Okay, so let's look at here. From the cross-sectional view, you can see that the top metallization layer is in this blue color. And then we have the second metallization layer here, which is in yellow color. This is the first metallization layer that we need to isolate later on. And for the resistor itself, it is made of a polysilicon. So now we have to determine which one is the area that we need to isolate. So basically, this will be the location that we consider to cut the connection, as I highlighted here in this white box. And after that, we can also add in the new wiring and also the prop pad for the connection. Okay, now this is the image taken from the top view of the sample after we have performed the circuit modification. You can see this is the position for the actual isolation. And here are the pads that can be used for the electrical guy to perform the electrical measurement later on. And this is the example of the results that we measured the IV to check the resistance value of this resistor. Okay, so that's the end for the case study 1. And now let's move on for the case study 2, which is embedded defect analysis. So what is embedded defect? So basically, embedded defect is a defect that is actually located beneath the surface and it is not visible from the top view. Like for the example here, it was reported that this device failed with electrical testing, which is suspected due to the embedded defect. So in order for us to confirm this report, so we have to perform the physical analysis and of course, the material analysis to determine the composition of the defect. And for the physical analysis, we can use the focused ion beam instrument to do the cutting on the sample so that you can view the defect from the side. And of course, if the defect is so small, we can also perform the subsequent sample preparation. We call it a lamella preparation, so that after that, you can inspect the sample using high transmission electron microscopy for high resolution inspection. And attached to this TM system, we have the EDS capability that will allow us to do the elemental composition. And at the same time, the equipment is also have the capability to perform electron energy loss spectroscopy for the chemical state of the defect. And so this is the result from the flip cut that we have performed on the sample. So from this result, it is proven that there is a presence of the contaminants at the interface of these two layers as highlighted here. And because of the defect is so thin, we have to proceed for the TM inspection. But prior to that, we have to perform the lamella preparation. So in this slide, I will explain to you the lamella preparation step. First, we need to do the two bulk cut. And at this stage, the thickness of the lamella is about 1 to 2 micrometer. And after that, we have to lift out the lamella with the aid of this probe needle. However, we are not able to directly transfer this lamella into the TM system because it is so small. So for that, we need to have another sample holder, which we call it the TM grid. So we do have the copper and also molybdenum type. And from this grid, there are actually 3 fingers here. So we can attach the lamella onto one of the finger. So the attachment here is by using the platinum deposition. And after that, the last step is basically to do the final thinning. Initially, the thickness of the lamella is about 2 micron, and we have to thin it down to less than 100 nanometer, which is transparent to the electron beam, so that the electron beam can transmit through the sample in the TM system later on. Okay, so this is the result from the TM inspection. So from here, you can see like different scale here that showing TM is capable in providing high resolution image. We can actually observe the texture of the defect here. We can also perform precise measurement of the defect. However, this is only a qualitative information. So we are not able to determine what is the element of this defect just by looking at this image. For that, we have to actually perform the subsequent EDS testing on the sample. And for the EDS analysis, we can actually identify the location for the EDS mapping. For example, as shown in the red box here. And from this analysis, it can actually generate the spectrum for us. Please also take note that there is a presence of molybdenum element in this spectrum, which is coming from the TM grid itself. And this is actually the result from the EDS mapping. And you can see this, the distribution of the elements with this different color here. And from here, we can actually conclude that the contaminants or the defect is composed of nickel and also oxygen elements. But as we know that EDS is meant for elemental analysis. So whether to prove that this is a real nickel monoxide or not, we have to perform the subsequent testing. We call it EELS, electron energy loss spectroscopy. So it's the same thing that we can also perform the EDS on the EELS on the defect, and we will obtain this nickel monoxide spectra from the EELS characterization. On the top layer here, there is a nickel layer, and it is also proven from this nickel spectra. And of course, for the EELS analysis, we always have to have the reference. And in this case, we are using the EELS atlas for us to confirm the oxidation state of this nickel. And from this analysis, we can conclude that the oxidized nickel at the interface of the two layers has caused a failure to this device. Now we move on for the case study number 3, which is copper oxidation analysis on bare copper lead frame substrate. So for this copper lead frame, the customer has subjected the sample to a heat treatment process at an elevated temperatures ranging from 150 degrees Celsius to 240 degrees Celsius. So now let us review what kind of characterization techniques that can be applied to study about this material. First, of course, we need to perform the visual inspection. So we can use high power optical microscope for this case. And after that, we can also study about the surface texture of the sample through field emission scanning electron microscopy. However, this technique is only a qualitative information. In order for us to measure or to quantify the roughness on the sample surface, we can also perform the subsequent atomic force microscopy analysis. The heat treatment process will also have the tendency to induce the grain growth. So in this case, we can actually perform focused ion beam analysis to study about the grain structure. We can analyze the grain from the top surface and also from the cross-sectional view by using this method. And of course, one of the important information in this study is to know about the copper oxide thickness. So in this case, we can actually perform the analysis using TEM, but prior to that, we have to prepare the lamella sample first. And another method that we can induce to actually check the copper oxide is by introducing Auger electron spectroscopy depth profiling. And this process does not require any sample preparation, but it will involve the argon ion sputtering. And of course, for the composition analysis, we can utilize EDS, EELS for the oxidation state, and we also have another option by doing XPS to determine the oxidation state of the copper oxide. So the next few slides will actually show to you the outcome of each characterization technique. So this is the result from optical microscopy inspection. And we can actually observe from here series of color change as the lead frame subjected to a different heat treatment process. You can see the change of color like this one, purplish, silverish, gold with some traces of green and pink color. However, the resolution in optical microscopy is not high enough for us to reveal the surface texture. And now, for that, we can actually perform the FSM inspection. So this is the result from the FSM inspection. You can see the change in the surface morphology from fine texture to a rough texture and also granulated structure on the surface here. But again, this is only for a qualitative information. For quantitative information, we can actually perform atomic force microscopy. It can provide to you this 3D roughness information. And at the same time, we can also obtain either RA or RMS value to actually determine the roughness of the sample surface. Like for this case, show to you actually the RMS value showing the roughness change for each sample. Now, for the grain growth analysis, we can also check from the surface and also from the cross-sectional view. And this process or information can be obtained by using focused ion beam instrument. In this technique, we are using the secondary ion imaging to reveal the grain structure via channeling contrast method. However, for the surface grain analysis, the sample has to be exposed to the ion beam first in order for us to reveal the surface grain. And after that, then only we can actually obtain this kind of secondary ion imaging. So the grain structure in crystalline material typically oriented at different angle. And therefore, the incident beam from the FIB will be penetrated differently at different depth. And therefore, it actually produces different contrast on the sample. And therefore, you can see either dark or bright contrast corresponding to each grains. And for the cross-sectional view, of course, we have to perform the feed cut first. Then only we can acquire the image by using secondary ion imaging. So the results that we obtain from here can be further processed using any grain size analysis software to calculate the grain size. Next is on the copper oxide thickness measurement. As highlighted earlier, we need to prepare the sample first using focused ion beam, then only we can inspect under TEM. And this is the example of the image that we can obtain from TEM. We can do a precise measurement, and at the same time, we can also observe the interface layer in between the copper oxide and also the copper substrate. Because of the TM has very high imaging resolution, we can also have this atomic structure of the copper oxide. And at the same time, we can measure the lattice spacing of the copper oxide. In this example, the spacing is about 0.25 nanometer, which is very small. And at the same time, we can also estimate the copper oxide thickness by doing Auger depth profiling analysis. And this process will involve the argon ion sputtering, and the etching rate is calibrated according to silicon dioxide standard sample. In this analysis, we will obtain this kind of profile. You can see the profile of copper and also profile for oxygen. And the estimated thickness of this copper oxide can be determined, like in this case, when the oxygen level is depleted. And in this case, the thickness is about 5 nanometer for this sample. And for the elemental composition analysis, we can perform EDS mapping, we can determine the location for the mapping, and we can get this copper mapping and also oxygen mapping. Same goes for EDS line scan. We can have this arrow that's showing the direction of the line scan, and we can also have the profile of the element across this interface. Okay, and for the oxidation state analysis, we can also obtain the CuO spectra, CO2O spectra, and even the spectra for the bulk copper. And for the XPS, we can also obtain the chemical state by doing this analysis. Like in this case, you can see there is a CO copper hydroxide on the sample surface. And of course, yields will require a reference standard. Same goes for XPS. A reference standard also is a must for us to determine the chemical state or the oxidation state for this copper oxide. That's the end of case study 3. And now let's move on for case study 4, which is surface contamination analysis on the battery tap. So here are the images of the battery tap. We have a good and bad sample here, and it was reported that the bad sample having high resistance issue. Based on the visual inspection, there is no discoloration observed on the bad sample, indicated that the contaminants could be very thin. Now, which one is the best analysis approach in order for us to analyze this contaminant? So look at this example here. We have the first option, which is EDS. However, if we use EDS, the signal penetration is about 1 to 3 micron from the sample surface. If we choose this option, there's a possibility that we are not able to determine the information of the contaminants because the EDX signal will be dominated by the bulk region of the sample. So what about the option number 2? We may consider for XPS. Well, for XPS, the signal information is about 10 nanometer from the top surface. So if you're comparing these two techniques, for sure, XPS is the best technique because it can provide better surface information than EDS analysis. For XPS analysis, you can perform XPS survey scan, XPS chemical state analysis, and also XPS step profile. So this is the result from XPS survey scan for the good and bad sample. So if we compare the detected element as tabulated here, we can see that there's a presence of chromium on the bad sample, but then not detected on a good sample. Additionally, we can also observe that the atomic percentage of silicon and also oxygen is much higher on the bad sample as compared with good sample. So from this data, it can provide to us the clue that the failure on the bad sample likely to be contributed by these elements. And in order for us to further confirm or understand about the contaminants, we can also perform the chemical state analysis. So we perform the chemical state analysis for chromium binding energy. And from this analysis, we observe that the possible chemical states are copper oxide and also copper hydroxide. So these two candidates could explain why we have high resistance issue on the sample because they are insulating material. And for the silicon binding energy, we observe the possible organic silicon information here. So this is also another candidate that could cause high resistance issue on the bad sample. Now, in order for us to estimate the thickness of these contaminants, we can also perform XPS step profiling analysis. So this analysis involves the use of argon ion gun, similar with Auger depth profiling analysis. So like in this case, this is the depth profiling result, and we can estimate the thickness of the contaminants layer here by looking at the chromium profile, which is about 8 nanometer. So the etching rate is actually calibrated to silicon dioxide standard sample. Well, that's the end for case study number 5, and this will be the last case study, which is surface contamination analysis on a lead frame sample. And this is the image of the lead frame sample, and it was reported that this sample experienced with non-stick on lead issue, which is suspected due to a surface contamination. For this analysis, we introduce time of flight secondary ion mass spectrometry technique. TOFSIMS is basically an extremely surface sensitive technique that the signal information is about few monolayers from the sample surface. The detection limit in TOFSIMS is in the range of part per million to the part per billion. It can also provide the information of organic and also inorganic material. However, the challenges in TOFSIMS is in terms of interpretation, and it can be much more complex as compared with XPS or OG techniques. Okay, so this is the outcome from TOFSIMS mapping analysis conducted in negative polarity. So how to read this data? So basically from here, we can see that there are some spots with higher intensity. So it actually indicates that for that particular area, we have high counts of that ion signal. Okay, and even we can have the data bar here, you can see that this data bar is in darker contrast, showing less count, and brighter contrast with higher counts. And for this analysis here, we can see many ion species that are actually related to these contaminants, yeah, as highlighted here. And at the same time, we can also show some other ion species that been detected on the sample surface, but not contributed to the contaminants. Okay, so this is some examples. Yep, so that's the end of my slide, and thank you for your attention.
Okay,
So,
yeah, Siti, I'll take over for the Q&A now.
yeah.
So just be there for us. Hold on.
Yeah, sure.
Okay, thank you. There are a lot of questions, more than 20 questions now. So we have two more presenter, but we'll try to entertain some of the question verbally. But for the question that we will not be able to answer due to limitation in time, we will follow up with you. I hope you can, the one posted the question can leave your contact number or email so that we can immediately follow up with you. Okay, one question that I would like to answer now, whether the tools in Mimos Kulim High Tech and Mimos KL is the same. Actually, we don't have any presence in terms of FA in Kulim yet. But we, as I mentioned just now, I hope I did not I hope you did not misunderstood me that we don't have any presence in Kulim in terms of the FA facilities, but we plan to have the setup soon in Kulim. So that's everything is in KL for the failure analysis services. The second question is regarding from Mahdi, from UM. He was asking about failure analysis for power electronic semiconductor, not only electronics. Actually, our failure analysis services are not restricted to only semiconductor devices. We receive, as I mentioned, multitude of materials for analysis, for example, like gloves, chemicals, and everything. So I hope Mahdi can also provide us your contact number so that we can follow up immediately for your requirement. Okay, Siti, there's a few questions related to your presentation. The first one is, what is the difference between EDEX and EELS? And in what case they are used for, EDEX and EELS? Maybe you want to answer that question first?
Yeah, I can. Let me open this slide here. Okay, so basically EDS and EELS both actually for material analysis, but for EDS, it can only provide to you the elemental information, which means single element. But the advantage of having EELS is that it can give you directly the information about the chemical state. It's no longer a single element, but at the same time, if we have single element, it is also possible to be done. So to answer your question, if you need to know the chemical state, then you can go for EELS. If this is not important, then you can perform the EDS analysis alone. And basically, EDS is meant for heavier element, and EELS is meant for light element.
Okay, related to FIB, which is expected, there are a lot of questions on FIB. Probably you can also share the sample, accepted sample dimension which can be accepted for FIB cutting. And also there's a question about how deep FIB can perform the cutting.
Okay, for our instrument, we can actually accept the sample with a diameter of 150 millimeter, and the height must be less than 1 centimeter. If let's say the height is higher than that, then you have to thin it down first, okay? And regarding the feed cut, of course, we can do deep or wider cut, but in return, the time taken for the process is very long, which also will induce higher costs for that process. So typically anything below than 100 micrometer can consider okay for the feed cut analysis, acceptable for feed cut analysis. If you need larger than that, then either we need a plasma feed or we can do the mechanical cross-section.
All right, hold on, there's a few more questions, but I would like to answer a question from anonymous attendee regarding how to differentiate ESD and EOS defect. Okay, for EOS, you can visibly see the burn mark, but for ESD, it's not as straightforward as that, and you would expect to see some pinhole at the active area. So that's my short answer. Probably, again, I wish that some of the answers that we cannot answer now, please help us by providing your details so that we can follow up with you. Siti, there's one question regarding using FIB again for circuit and circuit modification. Are we considering parasitic effect that could interfere the original circuit behavior, especially on the mixed signal circuit? So,
Thank you for the question, but I think we also have to take this question offline. We will answer it later on.
Okay, please,
Yeah.
an anonymous attendee who poses this question, please help us to give your details so that we can communicate with you. Okay, one more question. All right, both SEM and TEM are electron microscope, but why only TEM require lamella preparation?
Yeah, this is because of the principle of operation of each analysis is different. Like for SEM, we actually do the imaging from the top view. So that's why we do not need to do any sample preparation. But as for TM, the keyword itself also transmission, which means the electron beam must transmit through the sample. So we must have a very thin section, then only the electron beam can pass it through. So that's why we need to prepare the lamella first. If the sample is so thick, there is no way for us to see it in TEM.
Okay, great. So we are allowed to entertain a few more questions. Thank you. What is the difference? This is from Nur Maisara Abdul Rashid. Okay, what is the difference between OJ, electron spectroscopy, and XPS, X-ray photoelectron spectroscopy? This is the two surface analysis equipment. Which one is better for surface analysis?
Okay, so obviously the main difference, OJ is using electron beam as a primary source, and for XPS, we are using X-ray. So when we use electron as a source, usually we can have a very high resolution, which means for OJ, we can analyze the sample even though the size is in nanometer range. But for XPS, the lateral size of the area of interest has to be larger than 10 micrometer. So which one is better for surface analysis? It depends. If let's say the sample is conducting, both of the equipment can be used to do the analysis, but if the sample is insulating material, it's the best to use XPS because of it has the neutralization function to minimize the charging effect. Okay, and if let's say you're also interested to understand about the chemical state, for XPS, you have more a wider library as compared to OJ. So OJ library is only limited for the ionic bonding if you would like to understand about the chemical state. So other than that, you have the option depending on the lateral size of the analysis area.
Okay, thank you, Siti. There's one more question related to XPS from Subo Dubai. The question is for case study number 3. You use XPS and yields. Can you elaborate more what different of information we can get from yields compared to XPS?
Yeah. So the XPS analysis is performed from the top view. Let me open here. Where is it? So XPS analysis is performed from the top view. And for the yields, we can actually perform from the cross-sectional view. So you can also obtain the information under the surface, as we know that XPS detection is only about 6 nanometer from the top surface. However, yields technique will be much more expensive because we need to perform the sample preparation first. Like for XPS, you can directly analyze it from the sample surface. And furthermore, as mentioned earlier, that the probe size or the lateral size is quite large, which is 10 micrometer. But if we talk about yields in TEM, the area is very small. So it's actually critical if you have like a nano defect, nano size material, nano layers and so on. Yeah.
All right. Following to that as well, there's a question from Nora Yaakob. When you mention yields, can it detect light element? Does it include nitrogen?
Yes, yields basically it can detect from hydrogen to uranium from the periodic table. It can also detect nitrogen. The answer is yes. However, the sample preparation is quite challenging for yields because it has to be very thin.
All right. Okay. Again, XPS question from Nora juga. Can XPS and TOF-SIM detect different phases such as alpha and gamma alumina, or they can just detect elements?
Okay, so I think for the elemental information, of course, yes, it can be detected. But for another question, you also need to take it offline as well.
All right. Okay.
Yeah.
Again, Nora, help us to provide your details. I will just show the email address of the person that you, later on I will show the email address for the person that you can write to for your inquiry. I guess we'll stop here for a while. There's still a lot of questions coming, but I think we give the time to our distinguished speakers from overseas to proceed with their presentation. So Lawrence, can I pass it to you?
Okay. Wow, look at the session. It was pretty interesting. Well, there's many questions, and it's really interesting to see all our friends asking a lot of questions. That's good. That shows this is a very important subject, and there are many people who are really interested to know more. So please stick around. We have two more very interesting speakers that will be coming up. Just a quick plug-in for the organizers. Mimos Berhad and Cress has organized this webinar, and we'll be coming up with a few more in future. So stay tuned right till the end, and we have some very interesting announcements.